in the previous, in this example, we had a look at two displacement time functions for two different balls. And in these examples, we got to this point where we were putting our information into the displacement time equation. And then we had to consider this initial velocity, right? And we had the same thing where when we considered the time for the second object, right, we had to consider that we had this time, but it was time minus 2 seconds, right? Everything happened 2 seconds later. So I'd like to use some transformations that we've learned already to visually show you what's happening and why we actually do this. So I'm going to ignore the forces and we're just going to look at the equations themselves. So let's have a look at ball number 1. We had an initial velocity of 0 meters per second. We had acceleration equal to minus 10 meters per second squared. We were trying to find a displacement time function for this object, okay? And let's ignore the fact for now that we had this starting displacement of 30 meters. Okay, we could put the displacement of 30 meters. So if we consider the equation displacement equals ut plus a half t squared, if I put the 30 meters in there, I would be solving for time, but I want a displacement time function, right, to solve for displacement at any point in time. So I need to leave displacement as a variable. But also consider that its starting displacement isn't 0, right? It's 30 meters, right? Based on the fact that this ball that we are considering started 30 meters above the ground, okay? And we didn't consider its starting location as the starting point. We considered the ground as the starting point. If we'd considered the ground as the starting point, its location as the starting point, well, then we wouldn't need to consider any initial displacement. So if we ignore the fact that we have initial displacement and we just create a function of time, so we say displacement is equal to our initial velocity times time is 0 plus a half, we have minus 10 as our acceleration times time squared. Let me clean this formula up. This is at squared. This is going to give me a displacement function of minus 5t squared. Okay. So what I'd like to do is I want to go and show you on Desmos what this function would look like, right? Remembering that this function is going to give me a visual representation of what my displacement looked like from any point in time. So let's just plug for ourselves in here. We're just going to use y and x to represent, or actually we can go displacement is equal to, right? Our equation was minus 5, and this was with respect to time squared, okay? So I'm going to zoom this in a little bit. And this is the displacement function for the ball that we have come up with. And you can see that according to the graph, the displacement starts at 0 and goes to the negative, right? In other words, we're saying if we called the ground location 0 and up being positive, this is saying the ball has started from the ground and is now digging its way down to hell, okay, which is obviously not correct. What we want to imagine is actually our displacement started at 30 meters above the ground, okay, and just using some basic knowledge, and if you remember back to translations, what we actually want to do is just translate this graph up so that its intersect, right, its starting value is at 30, right, and so we're just going to add 30. We're going to translate the graph up vertically 30 units, right? Now I can see that my starting displacement, because remember, this is a visual representation of what the ball displacement is for every second in time, right? So I can see that it starts now at 30 meters above the ground, and its displacement decreases as it falls towards the ground, ending where it collides, right? And we can, if we really want to, we can, on Desmos, we can pinpoint that location. That intersect will actually give me the time at which this happens. At 2.449 seconds, the ball would hit the ground. Okay? But that's just a nice visual representation for you to show you that when we have these functions, right, what actually we're doing is we're creating the function and then we're translating it up to the correct starting location. So we've seen now visually that what we need to do is consider the starting location of this function, right? And that starting location was 30 meters above the ground, right? So an alternative way to write this equation so that we don't forget is that displacement is actually equal to, well, the initial velocity. In other words, at time 0, right? This is actually just my y-intercept of my graph, okay? And then we add on our change in displacement. So this is just the change in displacement, and this is just the starting displacement. Right, in the same sense, let's consider the function of the second ball. All right, so if we consider the second ball, we had an initial velocity of 5 meters per second. Right, we have the same acceleration, and we want displacement as a function of time. Okay, and so we would use the same displacement equals, let's use our updated equation, right? Where was the displacement at time 0? Okay, now if we consider how we calculated or how we set the problem up, we said that the displacement, the starting location is the ground, and the ball is on the ground, so therefore its displacement in the beginning is 0. Right, then we have plus 5 for the initial velocity times time, and then we're going to get minus 5t squared. Okay, so this would be the function that I popped out, right? If I wasn't considering the fact that this ball didn't move for 2 seconds. Okay, so let's hop back into Desmos, and we're going to have a look at this function, right? And see what we get. So again, we can say displacement is equal to 5, I believe it's t minus 5t squared. There's my displacement time function. Okay, so having a look at this graph, it sort of makes sense. We throw the ball up, its displacement goes from 0 to some height above the ground, which would actually just be the maximum, right? The turning point, which I can isolate. There we go. This ball would go to a height of 1.25 meters at its maximum, and then fall back down to the ground, and it would hit the ground again after 1 second. Except we need to consider this problem in relation to the first ball. This ball didn't move for the first 2 seconds. In other words, its displacement remained the same up until it was chucked at 2 seconds. Right, so I need my starting displacement, this origin point, I need it to be moved to time of 2 seconds, because that's when the event occurred. And if you remember back to when we did translations, if we want to move a graph horizontally to the right, we can. I'm going to use the variable a just for now. Right, it's going to be messy until I have, unfortunately, put the brackets in correctly. This is going to be minus, and we're going to have a squared, right? And I'm going to add a slider, right? And I'm actually going to make that 0 for now. This is our starting location, okay? So if we remember back to translations, what we're actually doing is we're saying, right, that starting time, that displacement, I want it to be, well, I want to keep it 0. I want to make it 0 up until 2 seconds because that's when we threw the ball. So what we do is we just translate the graph over 2 units. And now you can see that the displacement, right, if we ignore everything below the x-axis, we can see that the displacement for this graph remained 0 up until 2 seconds when it was thrown in the air and then came back down to the ground. And we now have, if it was thrown up and didn't collide with the other ball, at 3 seconds, so 1 second later, it would have landed on the ground again. Okay, and you'll notice that the height is still at 1.25. It doesn't matter at what point we threw it, right? The important thing is that the displacement remains 0, and you can see this visually by translation. Okay, we could have changed the question and said that if the ball was thrown 1.5 seconds after the first ball, and all that's happening is we are either delaying or speeding up our displacement. So when we're translating like this, we are simply delaying or bringing forward the time at which the event happens. Okay? And so based on that, we can go back to Desmos or to our equation here, and we can see that in order to get the correct time, we need to translate the graph over 2 units. So the displacement for this function is 5, right? I want to take t, right? And when we move to the right, we subtract 2. And we do that for all values of t, right? And that's how we end up with the equation 5t minus 2 minus 5t minus 2 squared. Okay? So hopefully by visually seeing the translation now, you can understand what is actually happening behind the scenes. And that was the algebraic. This is the visual, all right? If you consider that this graph is just a visual representation of displacement, right, during time, and you ignore the bottom half, just look at the little top part above the x-axis, and you can see that all we're doing is, right, depending on how long before or after we throw the ball, we can calculate its displacement in relation to time.